Welcome to AES Encryption with Numbers. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today, we're going to demystify AES encryption by using simple numbers and examples you can follow along with. Instead of talking about billions of years and astronomical numbers, I'll show you exactly how AES works using small numbers you can calculate on paper. Imagine you want to send the secret number 1234 to a friend. How do you make sure nobody else can read it? That's where AES comes in. We'll start with toy examples using single digits, then build up to show you how the real AES works. By the end of this presentation, you will understand not just what AES does, but how it does it. You will see the actual transformations that turn your data into unreadable gibberish and back again. Simple substitution, the foundation. Let's start with the simplest form of encryption, substitution. Remember those decoder rings from cereal boxes? That's substitution encryption. In AES, one of the core operations is called subbytes, which is just a fancy substitution. Look at our example on the slide. We have a simple rule. Add 3 to each number. So, 1 becomes 4, 2 becomes 5, and so on. If the result is bigger than 9, we wrap around. For example, 8 becomes 1, because 8 plus 3 equals 11, and we only take the last digit. This is exactly what AES does in its sub-bytes step, but instead of adding 3, it uses a special lookup table called an S-box. Every possible byte value, 0 to 255, gets replaced with a specific other value. The S-box is carefully designed so that small changes in input create large changes in output. To decrypt, we just reverse the process. If we added 3 to encrypt, we subtract 3 to decrypt. In real AES, there is an inverse S-box that reverses the substitution. The key insight is that substitution scrambles the values, but in a reversible way, as long as you know the rule. This might seem too simple to be secure, and you're right. That's why AES doesn't stop here. This is just the first of several transformations that, when combined, create unbreakable encryption. The power of shifting positions. Now let's look at the second transformation. AES uses shifting rows. This is like sliding puzzle pieces around. While substitution changes what the values are, shifting changes where they are. In our example, we have a 4x4 grid of numbers. AES always works with 4x4 grids, which is 16 bytes or 128 bits. The shift rows operation is quite simple. You leave the first row alone, shift the second row left by 1 position, the third row by 2 positions, and the fourth row by 3 positions. Watch what happens to our number 6. It starts in row 2, position 2. After shifting, it moves to row 2, position 1. The number that was at the end wraps around to the beginning. It's like a circular conveyor belt for each row. Why do this? Because it spreads the information around. If an attacker manages to figure out something about one position, this shifting ensures that information gets scattered to different places in the next round. It is like shuffling a deck of cards. The cards are the same, but their positions change. To decrypt, we simply shift in the opposite direction. If we shifted left to encrypt, we shift right to decrypt. The amounts stay the same. 0, 1, 2, and 3 positions. This perfect reversibility is what makes AES work. Mixing columns, the mathematical magic. Here's where AES gets clever with mathematics. The mix columns step is like mixing ingredients in a blender. You can't easily separate them afterward, but with the right knowledge, you can reverse the process. In our simplified example, we're showing how each column gets mixed. Let's use really simple math. We'll multiply and add numbers from each column to create new values. For instance, to get the new first value in a column, we might calculate 2 times first, plus 3 times second, plus 1 times third, plus 1 times fourth. Look at the example calculation. We start with column values 2, 6, 10, 14. We apply our mixing formula to get new values. The key is that we're not just moving numbers around or substituting them. We're mathematically combining them. In real AES, this uses something called Galois field arithmetic, which is a fancy term for math that works within a fixed range of numbers. It ensures that our results do not grow infinitely large and that every operation can be reversed. This mixing is crucial for security. It means that changing even one input number affects all 4 output numbers in that column. This avalanche effect, where small changes create big differences, is what makes AES so secure. An attacker cannot work on one piece at a time. Everything is interconnected. Adding the secret key. Now we come to the heart of AES, adding the secret key. This is what makes your encryption unique. Without the key, all the substituting, shifting, and mixing in the world won't keep your data secret. In our example, let's say your secret key for the first 4 positions is 5, 3, 7, 1. We have our data after mixing. 12, 8, 15, 11. To add the key, we use XOR operation, but for simplicity, let's show it as regular addition with wrapping. So 12 plus 5 equals 17, which wraps to 7. Then 8 plus 3 equals 11, which wraps to 1. And so on. The beauty of XOR, which AES actually uses, is that it is its own inverse. If you XOR twice with the same key, you get back to the original. Think of the key like a combination lock. All AES implementations use the same substitution tables, shifting patterns, and mixing formulas. But your unique key makes your encryption different from everyone else's. Even if 2 people encrypt the same message, their different keys produce completely different results. In real AES, the key is 128, 192, or 256 bits long. This is like having a combination lock with 39 digits for AES 128. The key gets expanded into multiple round keys, with one for each round of encryption. This ensures that each round uses a different part of your secret key. One complete round. Let's walk through one complete round of our simplified AES to see how all the pieces work together. We'll encrypt the message 1, 2, 3, 4 using our toy example. First, we arrange our data in a 4x4 grid. Since we only have 4 digits, we will pad with zeros. Real AES would have 16 bytes of data filling the entire grid. Our starting grid shows 1, 2, 3, 4 in the first row, with zeros filling the rest. Step 1: sub-bytes. Each number is substituted. Using our simple add 3 rule, 1 becomes 4, 2 becomes 5, 3 becomes 6, and 4 becomes 7. The zeros become 3s. Step 2: shift rows. We shift each row to the left. Row 1 stays put. Row 2 shifts 1 position. Row 3 shifts 2 positions, and row 4 shifts 3 positions. Watch how the pattern changes. Step 3: mix columns. Each column is mathematically mixed. Our simple mixing spreads the influence of each number throughout its column. Step 4: add round key. Finally, we XOR with our round key. This is where your unique secret gets woven into the data. After just one round, our simple 1, 2, 3, 4 has become completely scrambled. Real AES does this 10, 12, or 14 times, making it impossible to reverse without the key. Why multiple rounds matter? You might wonder. If one round scrambles the data, why do we need 10 or more rounds? Let me show you with actual numbers why multiple rounds create exponentially better security. After round 1, our input transformed into a new output, represented using hexadecimal notation. An attacker might notice some patterns. They might observe that consecutive numbers in the input created a certain pattern in the output. But watch what happens in round 2. That 7B9F goes through substitution again, creating new values. Then, shifting moves everything around again. The mixing combines these new positions, and another round key gets added. Now we might have E2C8. By round 3, any trace of the original pattern is gone. The diagram shows how each bit of input affects more and more bits of output with each round. By round 5, changing just one bit of input changes about half the output bits. By round 10, the tiniest change in input creates a completely different output. This is called the avalanche effect, and it is crucial for security. It means an attacker cannot work backwards step by step. They cannot say, well, if this bit is 1, then that bit must have been 0. The interdependencies become so complex that the only way to decrypt is to have the key and run the inverse operations. Think of it like scrambling eggs. 1 stir mixes things a little. 10 stirs? You'll never separate the white from the yolk again. Real AES versus our toy example. Now let's see how our toy example relates to the real AES. The principles are identical, but the numbers get bigger and the math gets more sophisticated. First, the size difference. Our toy uses single digits, 0 to 9, while real AES uses bytes, 0 to 255. Our grid is still 4 by 4, but instead of 16 single digits, real AES processes 16 bytes. That's 128 bits of data at once. The subbytes step in real AES uses a 256 entry lookup table instead of our simple add 3 inches rule. This S-box is carefully designed using mathematical principles to resist cryptographic attacks. Each byte gets replaced by looking up its value in this table. Shift rows works in exactly the same way. The only difference is that we are shifting bytes instead of digits. The pattern is identical. 0, 1, 2, 3 positions for rows 1, 2, 3, 4. Mix columns is where the biggest difference lies. Real AES uses Galois field multiplication. This is a special math technique that keeps numbers within the byte range. It is like our mixing, but with specific coefficients that provide optimal diffusion. The add round key step uses XOR instead of addition. XOR is perfect for cryptography because A XOR B equals A. You can add the key and remove it with the same operation. Most importantly, real AES uses much longer keys. Even the smallest key, 128 bits, is like having a 39-digit password. That's why it's unbreakable. There are more possible keys than atoms in the universe. Seeing AES in action. Let us look at some actual numbers from a real AES encryption to see the dramatic transformation. Do not worry about calculating these yourself. I want you to see the pattern of how thoroughly the data gets scrambled. We start with the word, hello. This word, when represented in hexadecimal, is a sequence of numbers. Already, you can see how letters become numbers within the computer. These 6 bytes are then padded with zeros to fill our 4 by 4 grid of 16 bytes. After the first round of AES, those recognizable values become completely different. Something like 9B, 2C, 15, 87, F3, 4A. There's no visible connection between H48 becoming 9B. That's the S-box substitution at work. By round 5, the values have changed again to something like. Notice how there is no pattern, no progression you can follow. Each round thoroughly scrambles the previous round's output. After all 10 rounds, for AES 128, your hello has become 16 bytes of seemingly random data. The only way to get back to hello is to run the process in reverse with the correct key. Without the key, those 16 bytes could decrypt to any possible 16-byte message. There is no way to know which one is correct. This is why AES is used everywhere from your phone to your bank. It turns readable data into mathematical noise that only the key holder can reverse. The unbreakable puzzle. Let's put it all together and understand why AES is considered unbreakable. Using our number examples, I'll show you the mathematical mountain an attacker faces. Imagine you intercept the encrypted message and you want to find the original message. You know it went through 10 rounds of substitution, shifting, mixing, and key addition. But here's the problem. Without the key, there are 2 to the power of 128 possible ways it could have been encrypted. To put that into perspective, if you tried 1 key per second, it would take an astronomical number of years to try them all. Even if every computer on Earth tried 1,000,000 keys per second each, it would still take an incredibly long time. But it gets worse for attackers. Even if they guess part of the key, the way AES mixes everything together means they can't work on pieces independently. Remember our rounds? Each bit affects every other bit by the end. There's no shortcut, no pattern to exploit. The example on the slide shows this visually. One tiny change in the key produces a completely different result. Change key bit 1, and output bits 7, 33, 67, 89, 103, and 127 might flip. Change key bit 2, and a different random-looking set of output bits change. There's no predictable relationship. This is why, after 20+ years, no one has broken AES. It is not just hard, it is mathematically infeasible. The numbers protect your secrets absolutely. Thank you for your attendance. Please consider subscribing to the channel.